So welcome to lecture 35 of MCS 472. So today we consider periodic steady state. So we are going to solve the heat equation once again, but now to study periodic inputs. We will apply the Helmholtz phasor method to study how deep we should bury something in the ground to shield it from temperatures fluctuations on the surface. So this depends on the material that we are using. So we will derive this model. So there are three parts in this lecture. Central is that we are solving the heat equation again, but we are studying the effect of a periodic input. Okay, so here is the problem. So if we consider the temperature on the surface of the Earth, then there are temperature fluctuations. So at noon, when the sun is out, or at least when it's daylight, it's warmer than at night. So we have thus a system with a periodic input, and the question is that how deep before these periodic inputs have decayed. So how long is a little bit misleading in this slide. So here are the questions again. This is a question that has many applications. So here are three examples. One can heat one's home with a geothermal heat pump. So a heat pump uses in the winter, pumps up the heat that was stored in the summer. So here the cycle is not day and night, but summer and winter. The summer and winter also applies to hibernation. So worms, they disappear from, well, they are earthworms. Generally, we don't see them. But how deep should worms go in the winter to prevent from freezing? Assuming that this is not a regime where we have a permafrost. And then there is also the construction. So the middle problem is if you are thinking about using concrete to use in your building. So think about concrete walls in an office building. How thick should these walls be? If you make them too thick, then it's like sitting in a bunker. If you take them too thin, then you may feel the effects of the heat of the hot temperatures outside. You may feel them too much. Okay, so these are the three problems, three types of problems that will lead to proposals for projects. So we will provide the mathematical answer in this lecture. So here is the picture that should become clear at the end of the lecture. We have the horizontal axis represents the depth in which we should bury something. So the depth here is kind of not to look at the dimensions too much. As far as temperature goes, the temperature fluctuates but around 10 with an amplitude fluctuation from plus and minus 10. So here you can think about degrees Celsius. So in the first hour, could be at 1 o'clock at noon, when the temperature is highest, almost 20 degrees, and then gradually the temperature goes down and then goes up again. So we have at the depth 0 is at surface, and then you can see that as we go deeper, the oscillations are still noticeable. So at 0.2 we still see the fluctuations, but the amplitude is no longer 10, but is actually has dropped significantly. Okay. What do we consider? We consider the heat equation. So the heat equation is central on this slide. So we have a function depending on space, which is here the depth, and we have time. So now we consider boundary conditions where we have on the surface we have a periodic input. We have a function for x equals 0 where the function fluctuates in time. So the omega is going to determine the frequency. So the frequency could be a 24-hour cycle, or it could be a yearly seasonal cycle. So the other boundary condition is that at infinity, so in some sense this is a very realistic model if you look at the Earth, infinity is not really infinity, but at a considerable depth, the surface temperature is not felt anymore. So you still have then a steady temperature. So our model uses idealized numbers. So the x-axis goes down into the ground, and the infinity, as we shall see, is actually not really infinity in the model. You could see it on the pictures as well. Okay, we expect that as a solution we will have a decaying amplitude. So we can write our solution capital U as a function of x only. So as the deeper we go, the less the amplitude will become. And then we will have a phase lag. So we will still see the fluctuation. But the argument of the sign is not simply omega times t, but there is a function that depends on the depth. So that's kind of the shape of the function that we would expect. Now, there's a problem with this, is that if you would try this, just substitute it in, then it will be hard to resolve for the two unknown functions. So we have an unknown function for the amplitude and an unknown function for the phase lag. Both are functions that are depending on x. So the first exercise is substitute. You can do it by hand, but you can also use SymPy. And SymPy might actually reduce this to then a problem in x, and you can try to solve for these two functions. And in some sense, when you are given an exercise, there always is a nice and a fine solution for this exercise. But here you should argue why it will actually not work. So the first proposed solution that comes from our first intuition will not work. Okay, so no problem here. Let us look at the solution proposed by Helmholtz. Helmholtz proposed the following. It's called the phasor solution. So we have the amplitude sitting in there, x over x, but then we have a complicated exponential in front of it, where we are having the oscillations with this exponential. The little I is the imaginary unit. So if we substitute this phasor solution into the heat equation, then we will get an ordinary differential equation. So in a way, this is very, very similar to the separation of variables that reduces a partial differential equation to an ordinary differential equation. Okay, so let us do this. So we have our heat equation. So at the left we have the partial with respect to time. So if we are substituting this in, so there is something that was left out, so the capital Y is left out here. So we are substituting this exponential times capital Y of x into this differential equation. That's why when we derive by time, the Y of x just stays there. If we derive with respect to x 2 times, the exponential in time just remains there, seen as a constant, but we have the second order derivative with respect to x. So if we write down then we have the two partials. If we now write the differential equation, the partial differential equation with the new left-hand side, and actually the left-hand side here is the right-hand side, because there is the I times omega that appears as the factor for the left-hand side, for the right-hand side. So with this phasor solution, we have a very simple ordinary differential equation that only depends on space. Very nice. Okay, how do we solve it? We've seen an entire chapter on ordinary differential equations. So, but if we forgot everything about this, SymPy comes to the rescue. So here is a Python session where SymPy is used. SymPy uses the capital I for the imaginary unit. We formulate our ordinary differential equation with the variables x and omega, using the little y, actually as the capital Y here, as a function y. Okay, so then if we take the derivative operator, then this does not appear, that does not disappear, so we can solve the ordinary differential equation for y of x. Okay, so SymPy does everything for us very nicely. So what we see is that we have a family of solutions. It's a second order differential equation. So we would need two initial conditions if we were to do this numerically. But symbolically, we see that SymPy came up with two symbols, C1 and C2, two constants independent of x, where we essentially have an entire family of solutions. So we have a collinear combination of two exponentials. And we see the plus and the minus x coming in. So that is going to be important. I wrote it down in our normal notation, where we would use the little I for the imaginary unit, capital I, as in SymPy. Okay, um, so what we actually want is exponential decay. As x increases, so we only consider increasing values of x. If we think about the original problem, the x-axis goes down into the ground. So we have to look into the real and imaginary parts of the arguments of the exponentials. So it turns out that we can write the square root of the imaginary unit. We can decompose it in a real and into an imaginary part. If you do not, so here I wrote down the formula, but you can verify this. If you square this, then you will see. So it's an exercise. You left this as an exercise. If you doubt this decomposition, then if you square the right side, that you will get the imaginary unit y. Okay, so this leads then to so the omega determines the frequency, so that is always positive, so we can take square roots of positive numbers. And then we see that we have a decaying exponential with the real part of any exponential with an imaginary argument. The real part will determine the amplitude of the complex function, or of the amplitude of the oscillating part. So there will be something that oscillates, that's fine with us, but what isn't fine is that the solution will exponentially increase. So that means that this second term here um, will have to vanish. At the end, at infinity, we must have zero. Um, and that cannot happen if you have here a positive real part. So here we are using one of the boundary conditions. We're going to simplify a little bit further. The C1, let's not worry about the initial temperature now, or what temperature range we are considering. We simply are normalizing C1 equal to 1. Okay, so we found now an expression for the capital Y that was used in the capital U, where the Y appeared in that phasor. So we proposed a phasor solution where the phase lag was absorbed into the exponential. So we have found the y of x. Have we actually also now found the capital X, the amplitude essentially of the phasor solution? Well, let's rewrite the capital Y, separating the real and the imaginary part. So we have a part that decays. So the square root of 2 divided by 2 is pulled into the square root of omega in both exponentials. And now we have something that decays and something that oscillates. Now the decaying part, we call this capital X of x, and the oscillating part is the phase lag. So yes, indeed, in our phasor solution, we have found the amplitude, capital X, and also the theta. So the theta is the x times the square root of omega divided by 2. Good, let's assemble everything. So we had our phasor solution in function of the capital Y. If we are writing the everything now forget about the capital Y. The capital Y was just an intermediary actor, so we no longer need the capital Y. We are working now with the phasor solution. We have the capital X, or the amplitude, and we have the phase lag. So we have found a product of two exponentials, one real exponential and one exponential with an imaginary part, which will take care of the oscillations. Okay, halfway this lecture, and we have a mathematical model. We have a solution, or a form of the solution to our problem. Let's see what we can do with this. Well, let's see what you can do with this first. So we have solved the Helmholtz phasor. We have solved the heat equation. Look again at the heat equation, but now with different boundary conditions. So we have a simple sine function on input, and we are now considering an interval 0, 1. So when we considered earlier the heat equation, we were applying the Fourier method on considering the decaying temperatures in a pipe filled with water, nicely insulated, except at the endpoints. Here what we actually want to consider is again a pipe filled with some water, if you like, and at one end we are going to bring in some heat. So at the sign at 0 we have this sign that goes up and down, we heat and cool, and then at the other end there the temperature is fixed at 0. So at the left we have minus 1 and 1, the oscillation, and at the right we have fixed at 0. So model this problem, use the Helmholtz phasor method to solve the heat equation with these boundary conditions. Okay, how are we going to apply this now? Well, we have the diffusion constants of a material, so we want to have that constant in there. Let's call that diffusion constant alpha. We introduce alpha in the phasor solution in the denominator, join it with the 2 when we divide omega, that defines the frequency. And with this alpha constant, there is the penetration depth, delta, that is the reciprocal of the argument omega divided by 2 alpha. Why is that? Because if the x equals the penetration depth, the amplitude has decayed to 1 over the exponential constant, 1 over e. So that means that the amplitude, the fluctuations of the temperature, they have dropped to about 37% of the surface temperature. So the words around the formula explain why this depth of penetration is a meaningful parameter. So you can look at the formulas. If you substitute x, so you want that the amplitude is 1 over e, and I should say that the 37% is kind of the maximum. So the second half here fluctuates between -1 and 1. So it doesn't mean that at the surface, so it means that you have the same surface temperature. No, it means that the surface temperature can be at most 37%. So at the penetration depth, the temperature can be at most 37% of the maximal temperature of the surface. So that also another way of saying this, it the maximum temperature is cut by 3, by a factor of more than, for almost 3. Okay, so this depth of penetration depends on the frequency of the input and also the material. All right, so let's simulate. So if we want to simulate, we will need to have somewhere some numerical values. So the delta is the important parameter, the depth of the penetration. So I'm going to, in the formula here, I'm going to change the delta. So I'm having the minus x over delta. So because the omega over 2 times alpha is the inverse of delta. So that is the amplitude. We idealized in our model, we put the constant C1 to 1, but that actually means now that we can pick any number, any constant in front of the amplitude. That's the constant A. And there's also the temperature at the surface. So for x equals 0, so that's the T naught. If you look for plots, so the e to I times something is the cosine of that something plus an imaginary part that we here throw away. So that's it then. So we have this function now that we need to plot and to look at. Here is numerical setup. So for a diffusion constant 1 over a million, for a period where we take a 24-hour period, but it's expressed in seconds, so then we have our frequency, the omega that is then computed from this, and we have an initial temperature, say a surface temperature of 10 degrees, let's think it's Celsius, and the fluctuations are also 10 degrees Celsius. Alright, so the next plots have been made with a Jupyter notebook. So here you see the temperature after 1 hour, then it declines after 9 hours. After 13 hours, we are almost at 0, and then it goes up again. So if I run time backwards, so we go like this, and then we can go like that. So if I play this like this, I have what looks like an animation. So it could be another exercise to actually build an animation. Okay, in half an hour I'm actually done with this lecture, so this goes very well. What is left for me is to explain one last exercise. So the formula that we used for plotting already looked very nice, but we can even more simplify, because the critical parameter, we have actually only one parameter, and that is the penetration depth. So with the penetration depth, we can actually answer our original question if we go to a model, a function that has only one parameter in there. So we can reduce the model if by just an expression in this one parameter delta, and the other letters that appear there, the x and the t hat, the little t hat, these are the two independent variables. So with this model, depending on one parameter, which depends on the frequency of the periodicity, typically either we consider the seasonal fluctuations over 1 year, or we consider the daily, the day and night fluctuations. So this is our original question at the bottom of the slide, and the two formulas provide a mathematical model. The justification why this model is meaningful is because of the heat equation and the Helmholtz phasor method. Okay, in essence, this lecture is over in half an hour. What is left now for me for the next 10 minutes is to say something about 3 proposals for projects. So this problem has 3 different applications. So we can look at an alternative way to heat a home. So we can heat a home with a furnace, either hot air or with some baseboards with water. But anyway, it's done with a furnace. But the alternative is working with a geothermal heat pump. So in this course we have seen cost benefit analysis. This could be another opportunity that if you did a cost benefit analysis for the second project, perhaps you want to do something like that again. But if you didn't do it, so this could be an opportunity to do a cost benefit analysis. Compare the operation of the heat pump. That will come with different installation costs than a furnace. So one might expect that the installation costs might be a little bit more expensive, but you may gain because of this phase lag in the and also the decay in the amplitude. So gather some data, look into the diffusion constant, how can this be justified, how deep is one burying this system. So there are 2 parts in this project. Use the model, and using the model is essentially using the equations that were used in the plots. The next project also has some real data in there. So one had the thickness of the adobe walls. So if you build your home with walls that are too thick, then it will be a little bit like a bunker. So you will never really experience the sun, because the flux of the sun will actually never get through it. What you actually want is that you do not want that. So during the so this was in the southwest, where it can actually get quite hot during the day. So you want that your walls protect you from the burning sun during the day, but then still towards the end of the day, the heat comes through, and this helps you for the cold nights. So use the model for the thickness of these adobe walls. Again, here there is a 24-hour cycle, um, where the depth of the penetration will depend on the material. So we have the simulation, but also gather here some actual data. And if you are, perhaps you're not so much interested in these adobe walls, but you can also look at concrete. Um, why is the concrete of that level? Um, okay, the last project, it's April out there. If you want to go out and start with your shovel and start digging, if you want to be out and about, you look for an excuse to start digging in your yard. Well, here it is. How deep should you dig to find some worms? Um, you can. So I'm kind of not really suggesting that for this project you go out, but look at some biological data. Worms, they live under the ground, and one would expect that as the temperature, depending on the temperature, that worms have a mechanism to actually know how the real nice depth that they should be. So you could also ask the other question. So if you are interested in finding worms, how deep should you dig to find worms? Say in any season. Okay, so this lecture went over quickly. I hope this was interesting. So I will not dwell on here too much longer. So periodic steady state is covered in section 5 of chapter 11 of our textbook. Um, and this is the third lecture on, no, it's the fourth lecture on partial differential equations. So we still have one lecture left on partial differential equations. So I thank you for watching this movie. I hope this was interesting.